Hey everybody, welcome to another Chem Complete episode, and we are doing more spectroscopy today because it seems to be what you guys are really interested in. So, I am going to work on our third unknown that we have here. We have solved two others of these, and if you want to take a look, we've got examples. The first one that really spawned all this and was popular was back in, I want to say like 2017 or 2016. And then this summer, I released a course on how to actually go through and solve these in very specific detail. So now, at the end of that course, I did another example, and now we're doing a third example here. So I'm slowly trying to get through some of these and upload them when I have time so that you guys have plenty of examples to work off of here. So this is going to be an unknown with mass spec, IR, carbon-13, and proton NMR, just like the course taught. And as a brief reminder, if you'd like to support the channel, go over to chemcomplete.com. We offer the full walkthrough guide. It's like a 40-some page guide that I wrote with additional practice problems and answer key. It's only $5. Okay, it helps to support the channel. Even if you can't donate, just go over there. Any traffic we get is appreciated, and as always, like the video if it was helpful, and if you comment, I will interact. I also take suggestions through comments. If you have something you don't understand, you want further detail on, I can make a separate video. But other than that, let's go ahead and get started. Alright, so the first thing that we want to do is get the degrees of unsaturation down. And we're going to do that using the molecular formula that we have here, C8H9NO. So the way that we would start that is 2 times N, where N is the number of carbons, so that would be 8, plus 2, plus 1, that's coming from the nitrogen, minus 9, and the 9 is the number of hydrogens. So if you're confused about this or where this is coming from, go back to the course and check out the degrees of unsaturation lecture. I will have links in the description, and at the end of the video, the suggested videos, I will have one of those going to the playlist for all of this. So you divide by 2, and if you solve for all of that, you're going to find 5 degrees of unsaturation. So this is already going to suggest that we likely have a benzene ring and then some other type of degree of unsaturation. So maybe we have a carbonyl, maybe we have an alkene somewhere, but we have to determine that based on further spectroscopy. So now that we have this settled, the next thing we can do is we can go to the mass spec and we can look at the mass spec. So 135 is the mass, and if you were to add up the C8H9NO, that would confirm 135 if you went in and got the molecular weights for each of those atoms off of the table. Now, when we look at this, 135 is the mass peak, and then we have 120 as the base peak, or the largest peak that there is. I also did a video on this, so if you are confused between the M+ peak and the tallest peak, or the parent and the base peak, we sometimes call them, go ahead and check that video out as well. So 120, what we want to do here is look at the difference between 135 and 120, and the difference between that is 15. So 15 is very common for a methyl group as far as fragmentation patterns go. So that would be suggestive of a CH3 group that is being lost during that process or that cleavage that's going on there. All right? Now, it's also important to look at when you're taking the difference between 135 and 92, because that's the other major peak here. So when we go from 135 to 92 and you take the difference there, you end up with 43. Now, 43, the most common fragment that we come across for 43 is going to be a carbonyl fragment. So you have something that looks like this, and specifically it's usually an acetyl carbonyl fragment. So it's going to have a CH3 with the C double bond O, and that will be a 43 fragment that is lost. So these are sort of leading to the idea that perhaps we have an aromatic ring with a carbonyl, specifically an acetic type group on it, an acetate group. So, with that being said, that personally is where I would leave the mass spec. I would continue forward. I really want to get to that NMR, especially if I'm against the clock on a test. So, I'm going to come up to the IR and see what I can gather in terms of functionality up there, or functional groups. And excuse when I'm turning the pages, I just have my notes here, make sure I don't oversee anything or forget something. So, when you take a look, we've got two peaks here that are well above the 3000 region. Now, this peak right here that I'm putting a dot by, that's also above 3000, but not quite as far. That's about 3100. And around 3100 is where we get signals for aromatics and double bonds. So it's very likely that we probably have that aromatic ring given the degrees of unsaturation. But again, I need to confirm that with some other spectroscopy. So we have further support here, and when we have a set of two peaks that are appearing this high up in the almost 3400 region, you got 3396 and 3334, it's usually one of two things. It's either an alcohol or it's an amine. Now, we do have oxygen and nitrogen both in the molecular formula. However, alcohols are very broad, rounded peaks. And the amines are much more medium, narrow type peaks here. And if I have two of them, it's going to suggest that I would have a primary amine, because when you have two of these peaks, you've got the N, and then you have this H, and you also have this H, right? So they can have a symmetrical stretch where they are both going in the same direction, and then they can also have an asymmetric stretch where one of them is going one way and the other is coming in the other way. So when you see those two types of splits up in that area, it usually is suggesting that we have a primary amine, so we have an NH2 group of some sort. That is what the evidence is suggesting right now based on the IR. Okay, now if you look over here, we did suggest through the mass spec that we probably have a carbonyl. There is a peak in the carbonyl region. 1662, okay, is a little bit on the lower end of that carbonyl spectrum. So it could be that we have an amide, or we could potentially have the acetic ketone portionality that is attached to an aromatic ring. Both of those are plausible at this point, with the aromatic ring playing into some resonance, which can do some shifting with the IR. So based on what we see here, we can pretty well confirm we have the carbonyl. We most likely have an amine of some sort that we are working with. We certainly do not have an alcohol. And then we also likely have an aromatic based on the 3100 point here that we see. So those are all useful pieces of information to start chunking the puzzle together. Specifically, if I have a carbonyl and I do have an aromatic, that accounts for all of the degrees of unsaturation that I need to account for. Because the ring would be 1 degree, the 3 double bonds in the ring would each count as 1, so that's a total of 4 once I have benzene. And then if I have a carbonyl attached to that benzene, that's going to be 5. So then I go ahead and I move down here. Let's start analyzing the carbon-13 at this point. So when we get to the C13, you want to ignore this peak right here, the solvent peak. Okay, this solvent peak comes from when you're using some type of solvent for the NMR, and that solvent, which is deuterated, okay, it can sometimes have proton exchange going on, so you can start to see some of the peak. And then with carbon, you can certainly see it if there's C13 present, and we're dealing with the carbon NMR right now. So that's marked. You would know with what solvent you're using if you were running this in a lab. You would have an idea and say, I know that I'm using DMSO. DMSO is going to appear around 40 ppm, and so when I see that clustered set of peaks there, I'm going to go ahead and ignore that as the solvent peak. You would know that going in because you know what solvent you're picking. All right, so if you take a look here, we do have a depth NMR. There are no inverted peaks here, so we do not have any CH2s associated with this compound. That's a useful piece of information for when we are trying to put together the final structure. There are no CH2s, no methylene groups. Okay, so I do have something that is pretty far downfield here. Upfield. Although I do have something far downfield as well. This right here is most likely going to be just an sp3 hybridized carbon. Specifically, I would guess that this is a CH3, given that it is appearing below 30, and the other fact being that the mass spec really suggested that we could have a methyl group based on that lost fragment of 15, and then the acetyl group, which inherently has a methyl group in it. So CH3 is most likely going to be this peak here. So what else do we have? Well, we skip over the solvent, and then we don't hit anything again until we get up to around 100 and I'm going to call it 113, 114, because this would be the 110 mark right here. So at this point, we are looking at aromatic region. Now this is very upfield, relatively speaking, for the aromatic region. So it means there's probably some strong electron donating groups that are present, and that would be further confirmation that we probably have an NH2 on the ring, because NH2 is one of the strongest electron donating groups you can have on an aromatic ring. And it would likely lead to a large upfield push in the aromatic region for the sets of protons that would be ortho to that electron donating group. So what we see here is the 200, the one that's up by 200 here, that is most definitely a carbonyl. That is way too high to be anything else. Okay? Now when you get close to 200, you are suggesting that this is most likely a ketone and not an amide. An amide is going to show up in the maybe 165, 170 region, whereas getting 195, 200, you're talking about aldehydes and ketones. So this is better evidence that we probably have that acetyl group that was suggested by the mass spec versus the amide that we potentially were debating in the IR. So when you take a look here, okay, you've got 4 unique carbons in the aromatic region. So that would suggest that it's a di-substituted ring, and the di-substitution pattern is probably going to be para because 2 of these quaternary groups disappear, and that just leaves 2 identical sets of carbons. And you notice the ketone also disappears. That is not present on the depth. So for those that are confused what I'm talking about this one right here, this one right here, which is the ketone, and this one right here. They are not present in the depth. And the depth does 2 major things that help us. Number one, anytime there's a CH2 carbon, a methylene carbon, the peak is inverted. It's found upside down on that spec. We don't see any inverted peaks below the baseline. So no methylenes for this. However, quaternary carbons will not appear in the depth NMR. And so if you look for these peaks, right, it's almost like those pictures where it says tell the difference, what's changed. These peaks that I've highlighted or circled in red here, they don't appear up in the depth. They're missing, which means that they do not have any protons associated with them. They are fully quaternary substituted carbons in a case like that. So this brings some pretty good information into the fold. We have an aromatic ring most definitely based on the carbon 13. We don't have any CH2s. We do have a methyl. We do have a ketone most likely. And we do have a di-substituted aromatic ring. We'll confirm if it's para using the Proton NMR in a second here. So speaking of which, let's go down to the Proton NMR. Now I have these integrated for you. If you were to need to do this and you just had the integrations there, you take a relative ratio. So all of these you can see are approximately 2, and then the methyl is 3 in a relative ratio to one another. Again, let's ignore the solvent residual peak. You also don't need to worry about the TMS. That's the internal standard over there. So that's not anything that we're going to concern ourselves with. Now, this integrates to 3 and is a singlet. So that would confirm that I have a CH3, and that CH3 is attached to something that is not going to split or have any proton neighbors. So a carbonyl is a very likely candidate, especially given that the ppm here, the chemical shift, is showing up. Let's move my screen down here just a little bit so you guys can see the ppms. There we go. Okay, so it's showing up here at about 2.3, and that's where I would expect a ketone CH3 to show up. So we skip over the solvent peak. Then we have this peak right here, and it says exchanges with D2O. When you see something that says exchanges with D2O, that's simply another way of saying this group is involved with hydrogen bonding, because hydrogen bonding groups will very readily exchange deuteriums for hydrogens when you get into a hydrogen bonding situation. So this most likely would be an NH2 from everything that we were talking about. There is an integration to 2, and so this kind of confirms the presence of NH2. Now, we said that one of the sets of protons on the aromatic ring is going to be near an electron donating group. And we can confirm that here. 7 is right around the middle of the road for aromatics. So when you look at an aromatic set of protons, if they're 7, they're sort of not, they don't have a whole lot of electron donating or a whole lot of electron withdrawing going on. The closer you get to 8, there's more electron withdrawing, which is de-shielding. And the closer you get to 6, the more likely there is to be electron donating behavior. So because this right here is around 6.5, we would expect that these are the protons that are ortho, or in close proximity right next to the electron donating group, which would be the amine, the NH2. And then you see this right here, this would be in close proximity to an electron withdrawing group. And these protons right here that are around, I'm going to say 7.7, those would be feeling the effects of the acetyl group, because a carbonyl that is directly attached to an aromatic ring has electron withdrawing properties associated with the ortho positions. So you put all of this together and you can see, okay, now these show up as doublets, the aromatics. So if they are doublets, this would very definitely confirm that we have a para-substituted aromatic ring, because then the neighbors, right, these protons right here, would have one neighbor, and they would show up as identical signals here. So one neighbor is going to split into 2 signals. You'd have a doublet because of the n+1 rule. Okay, and if that's confusing, I also have videos explaining splitting and the reason splitting occurs, the n+1 rule, what all of that means if you get confused as to why these split apart into different peaks. Right? So then we have NH2 would be in one corner, and then in the opposite corner we would have our carbonyl with a CH3. Okay? And that would be the structure based on everything that we've put together here. You want to go back and confirm that you match up with your original formula, that you didn't make any mistakes along the way. So if we were to look at this here, the ring itself has 6 carbons. We get 7 from the carbonyl and then 8 from the CH3. So do we have 8 carbons? Yes, because it's C8H9NO. So let's knock out the nitrogen and the oxygen. The nitrogen comes from the amine, and then the oxygen comes from the carbonyl. So those are both accounted for. Now the last thing we need is 9 hydrogens. We get 4 on the aromatic ring. We pick up an additional 2 from the aniline or the amine group up here. So that's a total of 6. And then you add an additional 3 for that methyl group. That is 9. This structure is valid. It has the correct mass, the correct formula. All of the IR functional vibrations match up for this. And most importantly, the carbon and the proton NMR support this. So this is the correct structure for everything that we saw here. So I hope that this was helpful for you guys. I will continue to try to produce these while I have time. These take a lot more preparation, scanning, putting together. I have to make notes to make sure I'm not skipping over anything as I do them. But I know they are very valuable and people appreciate these types of lectures. So I will try to keep these up as often as I can. So if you found the video was useful, go ahead and like. If you have any questions or you just want to show your appreciation, comment section is always available. I try my best to interact with every comment that comes onto the channel. And of course, if you subscribe, you will be up to date throughout the semester with everything that we're releasing. We're trying to push out a lot of content. And one final reminder, head on over to chemcomplete.com. You can check out the full walkthrough guide that I have put together. It has tables, charts, all sorts of guidance solving these types of problems. And it's not just for unknown spectroscopy, even though that's the most popular. We have other guides that are up and available for nucleophilic substitution and elimination, IUPAC naming, and there's more stuff coming out every month that goes by. So thank you so much for learning with us, and we will see you guys in the next lecture.